any complex number whose value, to find the value of a modulus z, we'll take it as a square root of a square plus b square, and it is always a non-negative real number. So for any complex number z is equal to a plus ib, we define z bar as a minus ib. Conjugate is nothing but changing the sign of your imaginary part. Hello everyone, a warm welcome to one and all. This is Yashruti ma'am lecturing in Vidhyaashram, the Temple of Excellence, Mysuru. In this session, we are going to study about the modulus, conjugate and multiplicative inverse of a complex number. So in the previous session, we have studied the set of complex number. So what is the necessary of the new set of complex number, because we doesn't find any solution whose square is a negative. So that's why we can't find any real number as a solution whose square is a negative. We find those solution in the set of complex number, and the complex number is written in the form of a plus ib, where a and b are real numbers. So we have already studied the algebra of complex number. In this session, let us start with these three important things. And multiplicative inverse is again a complex number when you multiply it with any z whose value will be equal to 1, which is the multiplicative identity in the set of complex number. The first one is here, modulus of a complex number. So what do you mean by the modulus of a complex number? So suppose I have a complex number a plus ib, then the modulus of z is denoted by mod z, and it is a non-negative real number, and it is defined as square root of a square plus b square. Suppose I have z is equal to 3 minus I. What is the value of a here? It is 3. What is the value of b here? It is minus 1. So modulus of z is denoted by mod z, and at the square root we have a square plus b square, which is nothing but 3 square plus minus 1 whole square under the square root. So it is equal to 9 plus 1. So the value equal to root 10. So this is the modulus of a given complex number. So any complex number whose value, to find the value of a modulus z, we'll take it as a square root of a square plus b square, and it is always a non-negative real number. Either it can take the values of 0 or a number greater than 0. Next, conjugate of a complex number. So for any complex number z is equal to a plus ib, we define z bar as a minus ib. We just only change the sign of the imaginary part to get a complex number. Suppose we have a complex number as 3 plus 4i, then the conjugate of this is 3 minus 4i. Or suppose we have a complex number in the form of 3i minus 2 here. Remember, the imaginary part is this one. So we need to change the sign of an imaginary part. So therefore, the conjugate is minus 3i minus 2. Suppose we have a number like only a constant, like z is equal to 4. So it's purely real complex number whose imaginary part is 0. Then there is nothing to change the sign because we have only the real part of complex number. So z bar for this complex number is 4 only. Let's z is equal to minus 7i here, which is a purely a imaginary complex number, purely imaginary because its real part is 0. So now since we need to change the sign of the imaginary part here, the conjugate of this complex number is plus 7i, that is 7i. Thus, any complex number in the form of a plus ib is written as a minus ib. If you have negative, change it as positive. If you have positive, change it as negative to only the imaginary part of the complex number. Multiplicative inverse of a complex number. Let z is equal to a plus ib be a complex number. Then the multiplicative inverse of a z is denoted by z inverse, and it is given by the formula conjugate of z over mod z square. So generally 1 by z we usually calculate it. Suppose if we have 1 by a plus ib, then we will rationalize the denominator. We will take the conjugate of this then we used to write it as a minus ib divided by a square plus b square. So this is in the form of a plus b, a minus b, which can be written as a square minus b square. But since I square is minus 1, for any complex number, if you have a plus ib, a minus ib, then it is always a square plus b square. And a minus ib is nothing but the conjugate of the given complex number, because z is equal to a plus ib. And here we have a square plus b square. We know that mod z is square root of a square plus b square. So squaring on both sides, we get mod z square is equal to a square plus b square. Thus 1 by z, which is nothing but z inverse, can be defined as conjugate divided by mod z square. So thus we can use this formula to find the multiplicative inverse of any complex number. The other method is very simpler. As you know, you can just rationalize it and write the real part and imaginary part separately and then simplify. So next we have write down the modulus of I. So here we have only the imaginary part. Real part is 0. That means my A value is 0. B value is 1 because we have I. I is in the form of 1 into I. And modulus of this complex number is again square root of a square plus b square. But a value is 0. So 0 square is 0. B value is 1. So 1 square is 1. So you will get it as root of 1. So modulus of z is nothing but 1. Now we have 3 plus I root 3. So here it is in the form of a plus ib, whose a value is 3 and b value is root 3. So let us take mod z as square root of a square plus b square. Value of a is 3, 3 square is 9. Value of b is root 3 whole square is just 3. So it is 9 plus 3, you will get it as root 12. And root 12 can be written as 4 into 3. Thus we can write it as 2 root 3. So this is the modulus of the given complex number. Next, find the multiplicative inverse of the following complex number. We know that z inverse can be written as conjugate of z over mod z square. So here let's find the conjugate first. Conjugate is nothing but changing the sign of your imaginary part. So therefore conjugate is here 2 plus 3i, and we need mod z square here. So this is nothing but a square plus b square. So without square root, this is mod z whole square. With square root, it is just mod z. So what is your a square? A square is 2 square here. And b is minus 3 here. So minus 3 whole square, which is 4 plus 9, which is equal to 13. Hence, here this will become 2 plus 3i divided by 13, or z inverse is equal to 2 by 13 plus I into 3 by 13. So this is the inverse of the given complex number. Next, root 5 plus 3i. Again, z inverse can be taken as conjugate of z by modulus z square. So conjugate here it is root 5 minus 3i, and mod z square becomes a square, that is root 5 square plus b square, that is 3 square. You will get it as 5 plus 9, whose value is 14. So therefore here it is root 5 plus 3i divided by 14, which can be written as root 5 by 14 plus I 3 by 14. Separate the real and imaginary part. So that is your inverse of the given complex number. Next, find the conjugate of 3 minus 2i, 2 plus 3i divided by 1 plus 2i, 2 minus I. To find the conjugate of any complex number, first it has to be reduced in the form of a plus ib. So first let us reduce the given complex number in the form of a plus ib. So we have z is equal to 3 minus 2i, 2 plus 3i divided by 1 plus 2i, 2 minus I. Now conjugate means we are supposed to calculate z bar. So first let us write z in the form of a plus ib. Let's multiply this. We will get 6 plus 9i minus 4i minus 6i square, and the denominator is here 2 minus I plus 4i minus I square, 2i square. So next we will get 9i minus 4i is 5i, I square, and we know that value of I square is equal to minus 1. So if you substitute I square as minus 1 here, minus 1 into minus 6 is plus 6. So 6 plus 6 is 12. So here it is 12 plus 5i. Next we have minus I plus 4i, which becomes 3i. 2 plus 2 is 4. 4 plus 3i. Now again in the denominator I have a complex number. So let us rationalize it to make it as some rational number. To rationalize this, let us multiply with the conjugate of 4 plus 3i. So what is the conjugate of 4 plus 3i? It is 4 minus 3i. Now let's multiply again the numerator and the denominator. So I told you any complex number in the form of a plus ib into a minus ib is nothing but a square plus b square, because we know the formula for a plus b, a minus b as a square minus b square, but here in the place of b square I have I square b square. When I substitute the value of I square, it will be equal to minus 1, hence here it will become positive, that is minus into minus 1 becomes plus. So therefore for any complex number of this form, the value can be taken as a square plus b square. Now here when you multiply it, you will get here, so 12 fours are, that is 48 minus 36i plus 20i minus 15i square whole divided by, so a plus b, a minus b means it is a square plus b square. So this is 4 square, which is 16 plus 3 square 9. Now on solving this, we will get the value of z as I square is here minus 1, minus 1 minus 15 becomes plus 15. So the value is equal to 63. So we have 63 minus 36 plus 20 becomes 16i divided by 16 plus 9 is 25. So z is equal to 63 by 25 minus I 16 by 25. So this is our z now. Now if this is z, real part is 63 by 25, imaginary part is 16 by 25. So what is the conjugate of this number? So therefore z bar is 63 by 25 plus I into 16 by 25. So this is the conjugate of the given complex number. So always reduce the complex number into the simplest form of a plus ib or a minus ib, then we can write its conjugate. Next we have, if x plus iy is equal to a plus ib divided by a minus ib, prove that x square plus y square is equal to 1. So I told you any complex number in the form of a plus ib, a minus ib can be written as a square plus b square. So that's why we have here x plus iy is equal to a plus ib divided by a minus ib. So therefore, let me take another a minus ib here. When I take minus I here, the equation here it becomes a minus ib divided by a plus ib. Just from this equation, instead of I, replace minus I. So I minus I, here it becomes minus I. If you replace minus I, minus into minus I becomes plus I. So interchange the signs here. So now multiply equation 1 and 2. So let us multiply the left hand side. We will get x plus iy into x minus iy, and here you will get it as a plus ib divided by a minus ib into a minus ib divided by a plus ib. Now this is in the form of a plus ib, a minus ib, which can be written as a square plus b square. So therefore on your left hand side this becomes x square plus y square. On right hand side you can cancel the terms here. So the value is equal to 1. Hence it is proved. If x minus iy is equal to square root of a minus ib divided by c minus id, prove that x square plus y square whole square is equal to a square plus b square divided by c square plus d square. Again, I'll use the same concept, that is, if we have x plus iy, x minus iy, we can write this as x square plus y square. Now we have already have this equation, that is x minus iy as square root of a minus ib divided by c minus id. Now replace I by minus I. Let me take this as equation 1. If you change I by minus I, then it becomes x plus iy. Here it becomes a plus ib, and here it becomes c plus id. So let me take it as equation 2. Now multiply both equations here. Then it is x minus iy divided by x plus iy, which is equal to square root of a minus ib divided by c minus id into square root of a plus ib divided by c plus id. Now on your right hand side, you can clearly write this as x square plus y square. Here you have square root, so it's a common root, so I can write it as a minus ib into a plus ib divided by c minus id, c plus id. So which is equal to square root of a square plus b square, because it is in the form of a minus ib, a plus ib, hence it is a square plus b square, and the denominator can be written as c square plus d square. Now you have x square plus y square is equal to square root of a square plus b square divided by c square plus d square. Now squaring on both sides, this will give you x square plus y square whole square is equal to a square plus b square divided by c square plus d square. Hence the result is proved. So squaring on both sides, you will get square here, square and square root cancels here. So we are left with the real numbers. Next question. If 1 plus I divided by 1 minus I whole power m is equal to 1, then find the least positive integral value of m. So here is a complex number given whose power or integral power is given as m, and the final value is equal to 1. So for what values of m, the given complex number takes the value as 1. First, let us simplify this complex number. So let me take 1 plus I and 1 minus I. Let us simplify this. To simplify this, I'll multiply with the conjugate 1 plus I by 1 plus I. Now here it is 1 plus I whole square, or 1 ones are 1 plus I plus I plus I square. Now here it is a minus b, a plus b, which is a square plus b square. So here it is 1 square minus I square. 1 plus I square is minus 1. Here you have 2i minus 1. I square is here also minus 1. Minus 1 into minus is plus. So here you will get 1 plus 1. 1 and minus 1 get cancelled. You will get 2i by 2. So 2 get cancels. You will get I. So instead of this, we can write I. So now consider 1 plus I divided by 1 minus I whole power m is equal to 1. 1 plus I, 1 minus I can be taken as I now. So therefore, instead of this, I'll replace I. Power m is equal to 1. We have studied the powers of 1, that is the least positive integer for which I is 1 is m is equal to 4. So here we need to find least positive integer value. We know that I is equal to root of minus 1, I square is equal to minus 1, I cube is equal to minus I, and I power 4 is equal to 1. And for every multiples of 4n, the value is 1. But 4 is the least positive integral where I can take the value of 1. So therefore here I power 4 is equal to 1. So therefore the value of m is 4. So in today's session, you have learnt about the modulus, conjugate and multiplicative inverse of a complex number and few problems related to it. We'll meet you in the next session with few more concepts. Until then, keep watching, keep learning, keep exploring. Thank you.